Okay, let's look at some more molecular geometries, and let's kind of do this from the beginning. Let's look at NCl3. Now, if we want to know what the geometry is, we've got to start with the Lewis structure. So, well, nitrogen's less electronegative, and there's 3 chlorines. So I'm betting that the nitrogen is a central atom, and we have the 3 chlorines going around it. I've already counted the electrons. There's 26 electrons, so let's put those in there, making sure we put in our single bonds first. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have 24 electrons in there of our 26. We've got 2 more electrons to go, but all the terminal atoms have their octets. Where do the 2 electrons go? That's right, up on the central atom. Now note, we already filled the octets of the terminal atoms. The central atom nitrogen, 1, 2, 3, 4, 5, 6, 7, 8, it has its octet. At this point, we're not going to worry too much about formal charge, but if you were worried about formal charge, you would note that the chlorines have 1, 2, 3, 4, 5, 6, 7. Well, chlorines normally have 7 valence electrons. Here's 7 when we're looking at formal charge, so they have a formal charge of 0. Nitrogen normally has 5 valence electrons, 1, 2, 3, 4, 5. No formal charges here on any atom in this molecule. Okay, but then what's the shape? Well, first question, how many electron groups coming off the molecule? 1, 2, 3, 3 bonding pairs. 1 lone pair means 4 electron groups. How do 4 electron groups arrange themselves to be maximum angle apart? Well, that would be 109.5 degrees for our tetrahedral geometry. So if we're just considering electrons, the tetrahedral shape would be the electronic geometry. But when we're considering the atoms, when we don't worry about the lone pairs on the central atom, what shape is this? Well, this is trigonal pyramidal. And we can draw it kind of like this. Just like we were drawing a tetrahedron, what I recommend you do is draw it like you would have drawn a tetrahedral geometry. One going up this way, one going out this way, one as a wedge coming out this way, one as slashes going back that way. Here's our tetrahedral geometry. Question, how are you going to know how to draw a tetrahedron? I don't know. You have to memorize it. Just memorize the tetrahedron and the way it goes. One up, one coming out to the one side, a wedge, and a dash. So there are our 4 groups. I'm going to put a chlorine here, a chlorine here, a chlorine here, and I'm going to put the lone pair up top. And this is trigonal pyramidal. See how the nitrogen's in the middle, kind of makes a pyramid with 3 chlorines as the base of the pyramid, nitrogen's at the top of the pyramid. Because recall, with molecular geometry, we ignore that lone pair up there. We don't count it. So that's our trigonal pyramidal geometry. Question, what is the chlorine-nitrogen-chlorine angle? Well, if it was purely tetrahedral, for example, if we had another chlorine up here, then that would have been 109.5 because it is a tetrahedral electronic geometry. However, recall that lone pairs take up more space than bonding pairs, so we'd expect this lone pair to kind of squeeze these 3 chlorines a little bit closer together, kind of squeezing them down a little bit. So we'd expect the chlorine-nitrogen-chlorine angle to be a little bit less than 109.5. Okay. Let's do our next one, our good buddy H2O. 8 electrons. Hopefully you can do the Lewis structure for this one really quick. We've done it already. So there is the Lewis structure. And for some reason, a lot of people make this mistake when I ask, okay, what's the shape of this? People look at this and say, linear. But is it linear? I mean, you drew it linear like this, but is this hydrogen really 180 degrees from that hydrogen? We need to use Vsepr theory. Question, how many electron groups coming off that oxygen? Well, we've got our 2 bonding pairs, and we have 2 lone pairs, so that makes 4 electron groups. How do 4 electron groups come off a central atom? This was our oxygen here. How do 4 electron groups come off? They come off as a tetrahedron, right? 4 electron groups is tetrahedral geometry. So I'm going to draw my little framework here of a tetrahedron. Yeah. So then where do I put the hydrogens? Where do I put the lone pairs? It really doesn't matter. Just for fun, I'm going to put the hydrogens in the plane of the paper. And I'll say, okay, there was a lone pair coming out here and a lone pair coming out there. All right, so then what's that angle? What's the hydrogen-oxygen-hydrogen angle here? Well, we know that lone pairs take up more space than bonding pairs. It's tetrahedral electronic geometry, so you'd expect this to be about 109.5, but then we remember these take up more space, these lone pairs do. So we'd expect it to be less than 109.5. In fact, it's around 104, maybe 104.5 degrees, due to the extra space and taken up by these lone pairs kind of squishing those two hydrogens together. But then what are we going to call this shape? Well, recall, although the electronic geometry is tetrahedral, the molecular geometry, we ignore the lone pairs. So if we ignore the lone pairs, what shape is that? Just the hydrogens and the oxygens? You may have seen it before. That is back to bent or angular. This is our bent geometry again. Recall we saw bent geometry with a trigonal planar electronic geometry, and one of those groups in the trigonal plane being a lone pair. All right. Next molecule, PCl5, 40 electrons. Okay, we'll put our phosphorus in the middle, and five chlorines. 40 electrons, so I'm going to say, okay, I know each chlorine is going to be bonded to that phosphorus. Okay, so here, let's put them in. Our chlorine here, 2, 3, 4, 5. There's our 5 chlorines. Let's put in our 40 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. There are all 40 electrons. Okay, so there's no extra electrons, no lone pairs on the phosphorus. First thing to note, that phosphorus has 5 bonds coming from it, which means if we're looking at this, 5 bonds, it has 1, 2, 3, 4, 5, 6, 7, 9, 10, 10 electrons coming off of it. Hey, what happened to the octet rule? Oh, that's right. Phosphorus, if you're looking at your periodic table, is 1 below nitrogen. Phosphorus is in the n equals 3 shell, the n equals 3 quantum shell. So it still has the 3d orbitals available to it, but they don't have any electrons in them yet, because when you're doing the electron configuration, you don't get to the 3ds till after the 4 s's. So phosphorus can have an expanded octet. It can have 5 groups around it. Note, NCl5 does not exist. There's no nitrogen with 5 chlorines around it because nitrogen cannot expand its octet. All right, and so the question then is, how do 5 things arrange themselves? Well, they do it like this. The geometry is called Trigonal Bipyramidal, where we have a phosphorus here. Let's put a chlorine straight up, a chlorine straight down, a chlorine coming off this direction here to the left, and then 2 more chlorines, one coming to the right, straight off to the right, but kind of out towards us, and one going back. Okay. Note if we look at the angles in this molecule, this chlorine, phosphorus, chlorine angle here is 90 degrees. Same as this one here. This is 180 degrees here. But these 3 chlorines are in a trigonal plane, so this chlorine, phosphorus, chlorine angle here is 120 degrees, as is this chlorine, phosphorus, chlorine angle here. That's also 120 degrees. So what you have here, essentially, is a trigonal planar group. The phosphorus and these 3 chlorines are trigonal planar, and then these 2 chlorines are perpendicular to that, one up here, one down there. And we call that trigonal bipyramidal. And when you have this trigonal bipyramidal geometry, this chlorine up here and this chlorine down here, the two that are 180-degree angle away from each other, we call those two axial. These are the axial positions. It's like the axis of this molecule. And the three that are in the trigonal plane, we call those equatorial. Equatorial, as in equator. So these are kind of like around the middle, around the equator of the molecule there in the equatorial plane. These two are axial, like in the axis. Okay, so trigonal bipyramidal, PCl5. Let's do SF4. Now when we look at this, SF4 has 32 electrons. Let's see how they go in there. So let's put our sulfur in the middle, and we've got 4 fluorines, and you're probably wanting to put the 4 fluorines around like this. This is totally fine. When you're doing a Lewis structure, realize though, the Lewis structure you draw might not be the geometry. 32 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay. Oh, I think I missed some. Oh no. Let me check this. What is that electron count again? Well, fluorine. There's a problem. Yeah. See, what did I tell you? If I put in 32 electrons here, if I had 32 electrons in here, this would be my molecule. And what shape would you say this molecule is? Oh, you would say, well, 4 electron groups, that would be tetrahedral. Turns out I miscounted my electrons. Oh my goodness gracious. What did I tell you about counting electrons? You learned it in kindergarten. Yeah, preschool. We call that the fluorine has 7 electrons. 7 times 4 is 28 electrons. The sulfur has 6 valence electrons, so it's not 32, it's 34 electrons. There are 34 electrons around that sulfur. So here I've got 4 of them. That makes 32 of electrons. I still have 1 more lone pair, 2 more electrons to go on that sulfur. Note, you just miscount the electrons, miscount by 2, it totally throws off the answer for the right Lewis structure, it totally throws off the answer for the geometry. We have now just seen how very important it is to count the proper number of electrons. Cool. 34 electrons in this guy. Okay, so, well, now we need to look at the geometry. All right, how many electron groups? 1, 2, 3, 4, 5. 4 bonding pairs, 1 lone pair means 5 electron groups coming off that central atom. How do 5 electron groups arrange themselves along a central atom or off a central atom? That would be trigonal bipyramidal. But one of them's a lone pair, and recall we have 2 positions with trigonal bipyramidal. We have the axial position and the equatorial position. It turns out whenever you have trigonal bipyramidal electronic geometry, but then you have lone pairs go equatorial. Lone pairs are always equatorial. So when I draw this, I'm going to draw my sulfur here. I'm going to draw the trigonal bipyramidal framework here with my wedge here. My dash is going back that way. My 2 axials are going to be fluorines. But my equatorials, one of the equatorial positions is going to be the lone pair. By convention, we're going to make this one the lone pair and put the 2 fluorines here. when you actually make the molecule, it doesn't matter. These three are in a trigonal plane, so whichever one you want can be the lone pair. But when we see this, when we draw it this way, when we make this a lone pair, that makes it a little bit easier to see our geometry. This is called the seesaw geometry. Note, not the teeter-totter geometry, the seesaw geometry, because if you turn this 90 degrees this way, you could have drawn it like this. If you ignore this lone pair here, when we do the molecular geometry, and you turn this 90 degrees, rotate it 90 degrees like this, so this fluorine is rotated over to here, you can see it's kind of like two legs here standing here, and these groups are kind of going, you can, seesaw, teeter-totter, whatever, like that. So this is the seesaw geometry. Okay, BF3, 28 electrons. I'm not sure, does it actually have 28 electrons? Well, yeah, it does, because fluorine has 7, bromine has 7, so 4 times 7 is 28. Okay, so bromine's in the middle. We've got our 3 fluorines for this bromine trifluoride. And 28 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Well, we've got the fluorines with their octets with 24 electrons, 25, 26, 27, 28. So there's our 28 electrons. And note, geometry. The electronic geometry, we've got a bromine with 1, 2, 3, 4, 5. 5 electron groups coming off that bromine means trigonal bipyramidal electronic geometry. So I'm going to put my bromine here, and I'll make my trigonal bipyramidal framework. Our wedge here and our dash is there. And so the question is, where do the electrons go? Well, recall, electron pairs go equatorial in trigonal bipyramidal electronic geometry. So in this case, I'm going to actually make the lone pairs here and here, and put my 3 fluorines here and here. And if you then rotate this 90 degrees this way, you would see that the molecular geometry, when we ignore those 2 lone pairs, looks like a T. So this is T-shaped. Trigonal bipyramidal electronic geometry with 2 lone pairs is T-shaped. And yes, you got to memorize all these. All right, so our last example here, SF6. Whew, 48 electrons. F, 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 4Fs, 5Fs, 6Fs. Let's put in those 48 electrons, see if there's anything on that sulfur. Deep breath. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Okay, we filled up the octets of all of the fluorines, and we put in all 48 electrons, so there are no lone pairs on that sulfur. Can sulfur have an expanded octet? We look at the periodic table, it's 1 below oxygen. Yes, the 3d orbitals are available for that sulfur. It can have the expanded octet. All right, so what is this geometry? Well, the name of this geometry is going to be octahedral, and there are several ways to draw it. I kind of like to draw it like this. Anyone remember drawing like XYZ coordinate axes? Like that? Well, that's essentially what we have here. You have the sulfur in the middle, and a fluorine straight up, a fluorine straight down, a fluorine directly to the right, a fluorine directly to the left, a fluorine kind of coming out at you, so we're going to draw a wedge, and a fluorine going back this way. It's simply an XYZ coordinate axis where we're going to draw the slashes for the line going back and the wedge for the line coming out towards us. And this is our octahedral geometry. Okay. So, in your book on page 446 is a nice huge table that has a couple more geometries that I'm afraid you're going to need to know, but kind of covers a lot that we have covered here today over these last couple videos, and gives some example molecules. So note, when you look at this table, you've got the number of electron groups, you've got the how many bonds, how many lone pairs, the electronic geometry, the molecular geometry here, the bond angles, and an example molecule here. So yeah, it covered everything we've covered here. Note, some things we did not cover as you get to the bottom of the list is what happens when you have octahedral geometry, electronic geometry, but you have more lone pairs. Note, we have a couple of different ones right here with 6 groups coming off the central atom with 1 lone pair. That would be square pyramidal geometry. 6 groups coming off the central atom with 2 lone pairs would be the square planar geometry. Okay, so that's enough for this video. We'll pick it up again with seeing if molecules are polar or not.